Okay, welcome. This is Physics 162 and a little introduction to electric charge while I'm at a conference this week. So my name is Kristen Larson and we will meet face-to-face on Friday. But until then, I wanted to give you a little introduction to what we're going to be talking about in this class. So if you have no experience with electricity and magnetism, don't worry. Most of us don't have intuition about it right off the bat. And so let's just start from the beginning. It turns out that there are two kinds of electric charge. There are positive kinds and negative kinds. And you can have a lot of charges in an object. So maybe if you have a lot of positive charges, then we say this has a big plus Q. We're going to use Q for charge. If, however, for every positive charge you also have a negative charge in there, then when you add all those charges together, we say that it doesn't have a net charge of plus Q, it has a net charge of 0. So positive and negative charges cancel each other out. So the first thing that should tell you, if you remember from 161, is that charge is a scalar. It's just a number and a unit. It's just a property that an object has. Now you're going to spend a lot of time in the lab talking about charge and the kinds of experiments we do to learn about charge. But where I want to start the lecture part of this class is talking about force. And I like doing it because in Physics 161, we talked a lot about force. So when you think about forces, hopefully you think about things like free body diagrams and arrows, and maybe you think about some components, with angles, and you choose some axes, because that's exactly what we're going to do. This is a new force. It's not like the other forces that you talked about in 161, but other than that, it has exactly the same properties. It's a vector, it has units like Newton, and you can add them as long as you add them like vectors. So this force is called the Coulomb force, after a person named Coulomb, I guess. And it goes like this, that the force between two objects is along the line connecting them. You'll notice that these two arrows are equal and opposite. That actually doesn't have anything to do with the Coulomb force. That's a property of force itself. That's Newton's third law. But the strength of these particular arrows, if you have a net charge Q1 and a net charge Q2 on these objects, the force between them is equal to some number that makes the units turn out right times Q1, Q2, all over the distance between them, R, squared. So the distance between their centers here is R. And that's pretty much it. So the force, the magnitude of the force, is the product of their charges, and it's inversely proportional to the distance between them squared. Okay, so far so good. Now there's a couple of extra wrinkles here, and one is that I mentioned something about this number that makes the units turn out right. And we're going to talk, it'll amaze you, I think, how many weeks will go by between when we first talk about this number and when we last talk about this number. Your textbook calls this K. I learned it as something much more complicated, which is 1 over 4 pi epsilon naught. Look, all you need to know is that this is just a number. We're going to use K for now. And since we don't do a lot of numbers in this class, we don't really need to know what that is, but we're going to come back to this. It's a number, and for what a Coulomb is, it's actually a pretty big number. It's actually a pretty big number. The other thing is that I should also talk about direction. So that's magnitude, the magnitude of the force. We should also talk about direction, and direction is a little more complicated than that, than maybe some of the other forces we've talked about. You might recall, say, for example, for gravity, we said the direction is really simple. It's downward all the time, all the time. The Coulomb force, Coulomb force can have two directions. They can either be attracting each other along the line connecting their centers, or, and I'll just draw two other random charges here, they can be repelling each other. So how do you know which one is which? Well, if you've ever heard that expression, opposites attract, that's what's happening here. If one of these has a net positive charge and the other has a net negative charge, they attract each other. Like charges repel, so either they're positive or two charges that are negatively net charged also repel each other. If they have the same net charge, just negative instead of positive, then that means that, well, if they have the same charge and the same distance between them, then they have the same force. So opposites attract and like charges repel. Okay, so I should mention one more thing, I guess, before I stop. And that's that if you've taken a chemistry class, you probably know a lot more about these charges. And for you folks, I'll just let you know or confirm what you already know, that the charges come in integer units of very small things. Charge, we say in physics, is quantized. And the smallest unit of a positive charge is the proton. And the smallest unit of the negative charge is the electron. And they're actually the same amount of charge. So if you take one proton and one electron, then you have zero net charge. So that's why atoms that have zero net charge, that aren't ionized, have equal numbers of protons and electrons. For those of us who aren't chemists, when we're talking about, a solid object like, a table, tables have gajillions of atoms. That's the technical term. And so when we're talking about net charge for a macroscopic object, something you can sit and have dinner at, what we mean is simply the excess over many electrons and protons. That's what gives it a net charge. Okay. But if you'll go with me on this idea of charge until you play with it in the lab next week, this week is assessment, but next week, we can start to do the same kinds of things that we've always done with forces, free body diagrams. That's exactly where we're going to start. So I will post that problem tomorrow. See you then.